Okay, in this one, we're going to look at a differential rate law. This one is called Deducing a Rate Law from the Initial Reaction Rate Data. In this particular example, we're not given the orders of the reactants. Some measurements of the initial rate of a certain reaction are given in the table below. So we are given the initial concentrations of two reactants. The first one is H2, hydrogen gas, most likely. The second one is I2, iodine gas. And then we're given the initial rate of reaction. So we'll assume that those are the two reactants. We don't need to worry about what the products are. We don't even need the balanced equation. We just need to know what the reactants are and what the concentrations are. In this one, we're not given any information about the orders of the reactants. So we don't know what the rate law looks like. So we have to figure out what the rate law looks like from this initial rate of reaction data. So as is common, you're given several experiments, 3 or 4 or 5 or 6 experiments. In this case, it's 3. We're given the initial concentrations of the two reactants. And then we're given the initial rate of reaction. So 3 different experiments. It's horizontal, you read across for each experiment. So in experiment 1, the concentration of H2 is 1.67 molar. The initial concentration of I2 is 1.20 molar. And then that means the initial rate of reaction is 46.0 molarity per second. Okay. In experiment 2, we change the concentration of H2. We decrease it. It's now only 0.418 molar. Notice the concentration of I2 doesn't change. We're going to keep that the same. That's a controlled concentration. But look what happens to the reaction rate. It decreased from 46.0 down to 11.5. What that tells us is that by making the hydrogen concentration smaller in the second reaction, we've decreased the rate of reaction. The second reaction is slower than the first reaction. And that's one of the primary findings of kinetics, is that changing the concentration of a reactant changes the speed of the reaction, the velocity or the rate. In experiment 3, now we go back up to the original concentration of H2. It's 1.67 molar. But now its I2 has been decreased. It's been decreased all the way down to 0.334 molar. And again, compare reaction 1 to 3. The initial rate went from 46.0 all the way down to 12.8. That's a very big change in the reaction rate. We will assume that it's because of I2. Changing the concentration of I2 changes the rate of reaction. So in this reaction, we're going to do a couple things. One is we're going to figure out what the rate law is, meaning we're going to figure out what the exponents are, but we're also going to find what the value of the rate constant is and along with its units. Okay, so here's how we'll go about it. I'm going to bring up the data here. So I'm going to number these for number 1. The H2 concentration is 1.67. I'll leave the units out for now. We don't need to worry about the units right now. The concentration of I2 is 1.20. And then the initial rate. It's actually the initial rate, but I'll just write R for, or I'll just write rate. Okay, 46.0. Okay, then I'm going to do number 2 here. It's 0.418, 1.20, and 11.5. So for right now, I'm just going to leave, just put 1, 2, and 3. I'll fill in 3 a little bit later. So here's what we'll do. I'm going to say that the rate of the reaction is the rate constant times the concentration of H2. And then I'm just going to put a variable, x. Sometimes it's an M, as in Michael. Sometimes it's an X. And then I'm going to put the concentration of I2 next to it. And then again, the exponent is a Y. So really our task in the first part of this problem is to figure out what the values of X and Y are. In general, X and Y are either 0, 1, or 2. Most commonly, it's a 1 or a 2. There are other possible values they can be, but for now, we're just going to leave it at the possibilities of 0, 1, or 2. Okay? So that's in general true for the rate law for this reaction. Now, for rate 1 is 46.0 molarity per second. And then what about rate 2? Rate 2 is 11.5 molarity per second. And here's what I'm going to do. I'm going to take a ratio of rate 1 to rate 2, R1 over R2. And here's what happens when you take R1 over R2. You get 3. You get 4. Okay, you get 4. So 11.5 divided by, 46 divided by 11.5. I'm just going to confirm that just real quick. 46 over 11.5. You get 4. Okay. Now what I'm going to do is I'm going to take the rate law for reaction 1. So that would be K. Now it's H2 to the X times I2 to the Y, where those are concentrations of H2 and I2. The concentration of H2 for experiment 1 is 1.67. Okay, so see what I'm doing? I'm just putting 1.67 raised to the X. I'm just plugging in the known concentration of H2 times the concentration of I2, which is 1.20. And that's going to be raised to the Y. Okay, so for this reaction, that would be the rate law for reaction 1. And I'm going to do the same thing for R2. Okay. And for R2, it's 0.418 to the X times 1.20 to the Y. Hopefully that makes sense. Just as I did up here, R1 over R2, I'm going to do the same thing here. R1 over R2. Okay. But look what happens. When you take the rate law for rate 1 and then rate 2, the rate constants cancel. K over K is 1. Furthermore, 1.20 to the Y divided by 1.20 to the Y, that also cancels. That's also a 1. So that leaves you with 1.67 to the X divided by 0.418 to the X. Now, there's a couple of rules of exponents, and one of them is if we have the same exponent for these two values, in this case it's X, we can simplify this and write it. We can put the bases directly into the parentheses and then just have one exponent on the outside. Okay. So it's like, if I have a to the X over b to the X, that's equal to a over b raised to the X. Now, the advantage of doing that is that now I can do the division inside the parentheses and you get 3.995. Okay. So now we have essentially determined that rate 1 over rate 2 is 3.995 to the X. But remember, back here where we took the rate data, we also determined that R1 over R2 is 4. So in other words, R1 over R2 is 4 which is equal to 3.995 to the x. Okay, see what happens here? Now, I said earlier that the value of x is either going to be 0, 1, or 2. So many of you will see this very quickly, but maybe you don't see it. If I take 3.995 and I raise it to the 0, that's equal to 1. And so if I was going to allow x to be 1, that's certainly not equal to 4, so that wouldn't work. It can't be. We know that x can't be 0, because if it was a 0, we would have 1 equals 4, and that's impossible. Okay, so what do we do? Well, let's try the next value. Let's put in 1. 3.995 to the 1. Well, that's 3.995. Now, is that equal to 4? Well, it's not exactly equal to 4, but it's pretty close, right? That's pretty close to 4. If I was just going to round it to the nearest ones, 3.995 would round to 4. So it looks like that's pretty good. Now, just as an aside, what would 3.995 to the second be? Suppose x was 2. Well, that's like squaring it, right? So that would be like 4 squared. That'd be approximately equal to 16. Clearly, it's not 16, it's 4. So what I did was I essentially did 2 divisions. You may want to watch this again. I took R1 over R2. I took the values over here. R1 over 2, just got a number. Then I took the rate law for the reaction R1 over R2. Canceled everything that would cancel. And what ends up happening is the only thing that doesn't cancel is the concentration of one of the reactants for both experiments. Then, based on the rules of exponents, you can write those 2 numbers in the parentheses, do the division, get a number, and then that's raised to the x. Then you come back to the ratio of the rates and set that equal to that base raised to the exponent. And then you just try your 3 different possibilities, 0, 1, and 2. Okay, it's going to come out pretty simply that it's one of them. It's either going to be a 0 or a 1 or a 2. If it came out to 1 to the x is equal to 1, or, if it came out to, let's say, 3.995 to the x equals 1, then you say, oh yeah, x must be 0 then. Okay, now we're going to do the same thing for the next one. So I'm going to go ahead and put in the third experiment. That's 334 and then 12.8. Okay, now what I'm going to do is I'm going to pick experiment 1 and 3. Now, why am I picking 1 and 3? Now what I'm trying to do is I'm trying to find out what y is. I'm trying to figure out what this exponent here is. To figure out what that exponent is, I have to see what happens when everything else cancels. In other words, the H2 has to cancel and the K has to cancel. In order for the H2 to cancel, it's got to have the same concentration in each experiment. So 1 and 3 would work, right? 1 and 3, the H2 is 1.67, so that'll cancel. Whereas the I2 won't cancel because you've got different numbers, 1.20 and 0.334. So I'm going to take R1 over R3, just like I did before. Now, people often ask, could you do R3 over R1? And absolutely you could. The math will work out a little bit differently, but you'll get the same answer. So R1 over R3 would be 46.0 over 12.8. Okay, now 46.0 over 12.8 is 3.59. Okay, now I'm going to do the same thing with the rate law. So you do it with the rate values, then you do it with the rate law. So R1 over R3, that would be K times 1.67 to the x. Now, technically, we know what x is. We know it's a 1. So if you want to use that value, you certainly can. And then we're going to do R3. R3 is 1.67 to the x times 0.334 to the y. K cancels. 1.67 to the x cancels, right? As long as the base is the same and the exponent's the same, it cancels. So that gives you 1.20 to the y over 0.334 to the y. which is 1.20 over 0.334 to the y. Remember, I'm just going to put it in the parentheses now. And if you do that division, you get 3.59. So nothing particularly exciting here. 3.59 is equal to 3.59 to the y. You can guess what y has got to be, right? Because again, 3.59 to the 0 would be 1. Now it's not equal to 1. It's equal to 3.59. So it must be equal to 1. So y must be equal to 1. Okay, so now we have the answer to the first part of the problem, which is what's the rate law? The rate is K times the concentration of H2. Now, when it's a 1, when the exponent's a 1, we just don't write anything. You know, because so for example, if I said, you know, like x, x is equal to x to the 1, but we don't write x to the 1, we just write x. So same thing here. If it's to the 1, just write H2. Same for I2. It's a 1, so just write it that way. So there's your notation, square bracket notation for concentrations. Now let's figure out what K is. To figure out what K is, now we know the exponents, we can figure this out. Because the rate constant K, if I divide both sides by the concentration of H2 and the concentration of I2, right? If I divide both sides by that, H2 over H2 would be 1, I2 over I2 would be 1, so you'd have rate over H2 I2, and that would be equal to K. Okay, so now what I'm gonna do is experiment 1, I'm just gonna plug our values in for experiment 1. So that would be 46.0 molarity per second over 1.67 molar over 1.20 molar. Okay, so that's rate over H2I2. You do the division there and you get a little bit, somewhere around 23. Okay, now what about the units? This molar will cancel with that. So I just have 1 over seconds. And I still have this one over here, so 1 over molar. So you write it m to the minus 1, s to the minus 1. It's an awkward, kind of weird notation, but that's how we do it. So what it means is 1 over molar, 1 over second. So I canceled one of the molars. We were left with one of the molars, but it's in the division, it's in the denominator, so it's 1 over molar. So m to the minus 1. Seconds is also in the denominator, so that's seconds to the minus 1. Now, what if I had done it for experiment 2? Suppose I did that one. Well, then I would have 11.5 molarity per second over 1.67 molar. Now, if this was 1.67 molar squared, you know, if the exponent were a 2, because we figured out that x was a 2, you'd put a 2 in there, you'd square it. 0.334 molar. And look what happens, you get the same value. So it's going to be the same for each one. Okay, I won't do the third one, but it's going to be the same as well. So it's 23. So for the second part, K would be 23. Be sure you put a decimal point after in terms of Alex. They want to have the decimal point in there. And then reciprocal molar, m to the minus 1, reciprocal seconds, s to the minus 1. Okay. And that would be our answer. Okay.